Okay, folks. So welcome to a Friday morning. So we ended up the last day, we had derived out a set of formulas here describing the behavior of these unslanted transmission gratings primarily. So this first order two-wave coupled wave model. And we described how we went through this, and specifically for lossless transmission gratings. And we went through our methods. And now I just want to show you what those R of X and the S of X, so the amplitudes, the magnitudes of the amplitudes of the diffracted beam and the transmitted beam look like inside these two types of geometries. So in the case of the transmission geometry, we have the input beam starts off high and then decreases as you traverse the unslanted transmission grating case. And the S of X, the amplitude of the diffracted beam, starts at 0 and grows up. And so you end up eventually where this will drop down to 0 and this will go up to 1. And so we have this type of behavior. And in the reflection geometry, we have the situation where we put in the beam and we have the fringes here parallel to the boundary, and we get this strong diffracted beam. In this case, what happens is our input beam decreases, the amplitude decreases as we go through the thickness of the hologram, and the diffracted beam actually starts at 0 here at the far end. So the S at X equal to D is equal to 0 or Z, and then, sorry, this should be Z and this should be Z and this should be Z and Z. We'll start at 0 and we'll increase back up here to this maximum value. So that's what's happening with these amplitudes inside these unslanted transmission gratings and this unslanted reflection type geometry grating. And we get this sort of behavior when we're on Bragg. If we look at the diffraction efficiency, and we sometimes talk about the growth curve. So if we monitor the actual diffracted intensity as we increase the modulation, so we expose and we watch the growth of the grating, we'll see this type of growth curve where again we start off with our transmitted beam, this cosine at 1, and then it decreases, and we have the diffracted beam starts off at 0 and it increases. And if we could imagine having a material in which we could continue to grow the modulation, so this grating strength, which is the N1 times D, and we could imagine that our exposure, we have an intensity pattern and we expose for a long period of time, then this axis will be the time axis. We would see the transmitted and diffracted beam changing like this. And once we go over this case here where the diffraction efficiency first reaches 100%, we talk about overmodulation. So we've overmodulated the grating. We've gone beyond this 100% point. Now again, this is a theoretical result, and we have to be careful because of course in the real world, we're going to have a lot of material effects that are going to be taking place. And so in general, we're not going to see this perfect type of modulation, this sinusoidal variation, where we've got this periodic variation as we change N1, as we lengthen the duration of the exposure. And again, this is for the case when we're on Bragg. So our dephasing parameter is equal to 0 and our off Bragg parameter, the Z, is equal to 0. If we then take, for example, this point here where the diffracted beam value is 1, okay, for the on Bragg angle, and then we change the angle of replay, we're going to get this general type of characteristic where the diffracted beam, the efficiency will decrease as we move away from Bragg, and the transmitted beam is going to increase. So this red curve here would correspond to the R, just as it does here, and this blue black curve is S. And we have a diffraction efficiency which will go from 1 and decrease down, and we notice here we have a 0 here, and we have a first side lobe. And we note that the total power, the efficiency in both of these beams is going to be conserved. We have a completely lossless perfect situation. So we've got this power conservation. And again, that's something that won't happen in the real world. So at this point here, we have our dephasing parameter on Bragg. Dephasing parameter is equal to 0, off Bragg parameter is 0. And as we decrease the angle or increase the angle, in both cases, these parameters, the magnitudes of these parameters are going to increase, and we'll move further and further off Bragg. And again, we recall this idea of the thick and the thin gratings, and we're going to come back and I'll talk a little bit of where these parameters come from. We're going to meet them. Certainly, if you go and read the Sims book, the reference I gave you earlier, you'll see that these actually appear out of the analysis of the diffraction equations. And we look at these thin and thick regimes also, I had a general comment here about the actual off-Bragg deficiency curves. We can come and we can actually look at these, we can simulate them, or we can do experiments. These are simulations. And we will see that for our thin gratings, we get this type of characteristic. And again, this here is the 0. This would be normal incidence. And this here would be the 2 Bragg angles. So we have an unslanted transmission grating. Yeah, so therefore we have these 2 on-Bragg conditions if we move either side of the normal incidence. And for our thick grating down here, we're going to see these very narrow type of characteristics, and both the diffracted beam and the transmitted beam are shown here, just as I did here. And as we move into the intermediate regime, we get this sort of mixture effect. So we don't have this strong Bragg effect. We have certainly a lot that's scattered, and depending on how far we are into the move from the thick into the intermediate regime, we'll get multiple cross couplings. Okay, so there's certainly some selectivity, and there may be quite a number of different diffraction orders. So here we quite clearly have a transmitted and diffracted order. Here we have a jumble of different orders. Here's our transmitted beam, and we can see that down here we have a lot of the power goes into all the various diffraction orders, but it's not narrow, it's not very selective. And on the other hand, once we get to the thick gratings, we have these plus and minus 1, plus and minus 2 diffraction orders. Here's our transmitted beam, and we see that in here, yeah, we have very little selectivity. If we change the angle in here, we vary the replay angle around the normal incidence, we see that the values of these diffraction orders don't change a lot. For example, if we look here at the plus and minus 1 and the 0, there's a big flat region in here where we're changing the angle, but we're not changing the diffraction efficiency in the plus and minus first diffraction order. And we've got a maximum value here, which is coming in about the 35 or the 40%. So again, these general characteristics in going from the thick grating to the thin grating via this intermediate regime. So the assumptions we've made, and again, just to be clear about this, because these are going to reappear, and they're particularly significant when we talk about this Cognix type situation. It's assumed that all the higher orders are negligible. We talked about this sigma plus k and the rho minus k. We only take into account, for the Bragg case, we only take into account the 2 waves. This would be consistent if we are sure we are in the thick regime. So self-serving statement. Yeah, we go in a circle here. But if we're in the thick regime, it's good approximation. It's assumed the second order derivatives are negligible. It's acceptable is, as we stated, energy transfer is slow inside the grating, and also includes a whole set of assumptions about the nature of the boundary condition problem being solved. When we neglect the second order derivatives, we're assuming the grating fills all space. Okay, so again, I gave you this diagram before. We have the grating in all space. We have a z is equal to 0 plane, a z is equal to d plane. We set up some initial conditions here for this unslanted grating, and then we find out what we would have at this dashed line inside this infinite volume. When the boundary conditions are applied, it was assumed that the R, for the transmission case, that the R value, the amplitude of the transmitted at z is equal to 0 was 1, and the diffracted value at z is equal to 0 was equal to 0. And in the reflection case, this switches. We'll talk more about that. If the second derivatives were retained, 2 boundary conditions would be sufficient, and 4 would be necessary, and not only the E field, but also the H field would have to be matched across the boundaries. And again, we're going to come to the rigorous case, and in the rigorous case, I'm not going to stress these points. I'm going to assume that you accept these. So I got a little bit here about the terminology and what we've talked about. We've talked about the index, yeah, the modulation, the interference pattern, exposure, what's diffraction, what's the grating equation, what's the Bragg law, that these don't tell us anything about the intensity. What are thick and thin? We haven't given the maths, but we've given the formula which govern it, and we've given you examples. How do we use complex amplitude transmittance? So this very simple single scatter type model, a kinetic model, a wave plane in 2D, and the evil circle. We're going to be using these as we go through, recording the grating, the interference pattern, the evil circle, and diffraction gratings on and off Bragg, general vector wave equation and scalar wave equation, the Cognix method and how he went about solving this, making various assumptions. Second order, first order, 2-wave, couple wave theory, and the evil diagram associate, for example, the flow K condition, how we describe the E field in the volume. Cognix derivation of the difference equation, Cognix on Bragg and off Bragg, and Cognix set of assumptions. So that's what we've hopefully now achieved. And I will circulate those notes to you later today. Okay. Now, Again, the emphasis here so far has been very much on Cognix and on Sims to flesh these things out. What are we going to do here? Well, we want to revise the work done on the first. Well, we don't have to do that so much. We're fairly clear on that, but we want to be clear, make sure everybody knows what's going on. We want to develop this model further to allow for slanted gratings. So we talked a little bit about that before. Now we're going to do it a little bit more in detail. And part of this too is a rhythm, that you just get used to the process by which we do this calculation using these coupled wave models. So you get basically very familiar with them. To examine the effects of moving off Bragg, theta, and wavelength for gratings with different efficiencies, and to examine the meaning of power conservation and diffraction efficiency. And again, I sort of indicated to you I was going to just talk a little bit at the beginning of each one of these things about something we've been doing in-house. One of the things we're very interested in is building systems for imaging and measuring motion. And one of the things we've been interested in measuring motion of is the human eye. And part of the reason for this is because the motion of the human eye comes from the brain. The eye is actually classed as part of the brain. And using measurements, accurate measurements of the motion of the eye, we can actually find out things about neurological disorders. So we built, for example, point systems. This is a holographic interferometric system here. We have two illuminations onto the surface of the eye, and then we get scatter, diffraction back in this direction from the two. And as the eye moves, we'll actually got a variation at this point detector, a variation in the intensity, which is related to the motion of that surface. That's a point type system. We've also built a camera-based system, and we're particularly interested in a type of motion called ocular microtremor. This is a relatively high frequency biological motion, so it's about 100 hertz, and it varies in size from tens of nanometers up to a micron or so. And by analyzing the frequency content of this motion, you can actually get information about, for example, if people are tired, if they drank coffee, and early warnings about neurological disorders like Parkinson's. So again, we've built these systems in collaboration with partners in the hospitals, and the idea is to be able to detect early onset and also detect efficacy in drugs. Okay, so back to what we're talking about. Here's our slanted grating, all our notation we made previously, our interference pattern, our description of the exposure, the dose. So we have the exposure time, the intensity, and some material parameter, and we've got this cosinusoidal variation, which includes this term here. And again, inside this information, we have the replay condition. In the previous lectures, very many ideas were introduced. So we had a lot of different concepts and ideas introduced. As far as the theoretical method, which can be applied to many situations. Perhaps the most important idea introduced in the lecture was that Cognix two-wave theory. As I said, pretty much everybody who does holography and volume holography starts off with Cognix theory. It's often referred to as K-vector closure, as we talked about, because of this flow K condition, this closed triangle that we see on our evil diagram. So the procedure used to derive the differential equation and the solution for this method, we've got to recall that, yeah? If you do not, it's okay, but we will first do a little revision. So just to remind ourselves of what we've been talking about, make sure everybody's very clear. And I'll go through this fairly sharpish, okay? Sorry, no. I'm in a sort of some sort of funny edit mode here, which I wish I wasn't in. Let me see. Okay. Well, we keep going anyway, so we'll see how we go. Okay. So again, here's our unslanted, and here's our evil diagram, and we can see here we've closed our triangle. We're on Bragg replay for this case, and we've got the grating vectors parallel to the grating boundary, unslanted transmission. We've derived solutions for this, and we've got out our three forms that we just spoke about, our thick, our thin variation. Sorry, this is annoying now, but okay. So we just talked about that. So what have we got? We've got our wave equation. We've got our wave equation. We've got the general case when the phi here is not equal to pi over 2. We do have slanted grating. And in that case, our k is going to have an x component and a z component. It's not just going to have an x component. So we're going to have variations along the boundary. And our permittivity is going to look something like this. Again, we're going to substitute that into our wave equation. And again, we're going to assume exactly the same type of variation. In the two-wave expansion, we're going to assume we have simply got the two components. In our higher order, we're going to have to put in an integer here, and our diffraction order is going to be equal to the input minus I an integer times k. We can plus or minus I here. So it's somewhat arbitrary whether we choose this I, the plus and minus values for the diffraction orders. But as long as we're consistent, it's going to be perfectly okay. So this type of expansion, we've talked about this flow K and the solutions of Matthew and Hill's equations. Here's our slanted grating, transmission grating. Here's our S at D and our R at D. And we can write down this more general type of graph here for the slanted case. Here's our K vector, and we say it closes the triangle. And then this would be the higher orders. This would be if we treat this as an input beam, this is our -1 and our +1 order, and this would be a -2 order here. And we see these are very, very far off Bragg. Okay, they're very far off Bragg. We can't simply drop a line here parallel to the z-axis or the kz axis and touch the circle. So these would be the higher orders that we will neglect, that we will assume have very little power in them. In this figure, we see on Bragg, and we can also do off Bragg. And here we see we've got an input beam at a different angle. Here's our K vector, and the K vector does not change. And now we're very clearly very far off Bragg. So this would be closed. This would be the form we get for closing the vector, the flow K condition, and we'd expect that beam to be traveling at an angle something like this outside. In that case, we're only interested in the Kx component of the K vector. That would be what would be important for the grating equation. So this is what we use inside the grating, and this would be what we would expect to see outside the grating. So we see off Bragg replay. And again, I've shown you this diagram before. And what do we have? We have our various on Bragg slanted transmission and reflection, and our off Bragg with angle, and our off Bragg with wavelength. Substituting for EY again into our scalar wave equation, and we get the second order formula. Again, both of them multiplied by these terms, and therefore both of these places inside the curly brackets have to be equal to 0. We're going to neglect the higher orders, want to keep the low orders, and so we end up with these two separate second order differential equations equal to 0. We neglect our second order derivatives, and so we end up with the following first order equations. And those first order equations, now we note, have got in them this rho z over beta. And here we have the sigma z over beta. So these are our obliquity factors we mentioned previously, and they arise because of the fact we have slanted gratings. And again, we're going to have the same type of dephasing parameter. For the unslanted case, this is going to be equal to this is equal to cosine theta. So we've got a very simple formula. We simply have a cosine theta in front of these first order derivatives. And typically we actually divide those across the form. So we're just left with the first order derivatives here. And so we end up with this kappa divided by cosine. And we end up with the dephasing parameter and the kappa here divided by the same cosine theta as we have for the slanted case, in the unslanted case. But in the slanted case, it's slightly more complicated. It's not simply so straightforward. There will not be so because of our use of the flow K condition. Because our angle inside, this rho divided by beta, that's not going to change, that's our input. But our sigma divided by beta is going to change because we've used the flow K condition to decide what the actual direction of the plane wave is inside the volume. So our sigma, we're going to have this two components. These are going to be our two components, beta times this and beta times this. And we can see here we no longer have cosine theta, we have this extra term here on our obliquity factor. And so we can come along and we can define this as being equal to this, and that's what's going to appear. So this is the same as for the unslanted case, but now we have a variation here on the obliquity factor because of the flow K condition. And we can do this out nice and neatly. We can draw this little diagram and we can make this all very specific here, but we've got to be aware of that. This is going to have other consequences in terms of the diffraction efficiency or calculation of the diffraction efficiencies. So this notation is usually used, and CR and CS are called the obliquity factors or slant factors. It should also be noted that replaying the grating at either of the two recording angles, so we put two beams in, and if we will play at the angle associated with any of those two beams, we're going to be on Bragg. It's going to give us an on Bragg response. So using these vector definitions, we can recall, and we did this little piece of math before, the cosine of the slant minus the theta, the replay angle, is equal to this k divided by 2 beta. Theta is either of the two on Bragg, so these are the Bragg angles. And the two coupled differential equations become this, simply using the obliquity notation. And again, we can go about it. We put in our substitution for the E field. We've got the R and the S. And so we then say our R has to have this form and our S has to have this form. And we substitute back into the equation, these first order coupled equations, to find analytic expressions. Okay. And we can come along and we can derive these. We can draw on our beams and clearly come up with this slant angle and expressions for the slant angle based on the fact that these fringes bisect the traveling directions of the angles of the two beams. So even if it's unslanted, this dashed line still goes split down. It's basically that plus that divided by 2 on either side of this angle. So it's a line of constant index. The recording setup with input angles theta S and theta R, the line of constant index is parallel to the interference pattern of the two planes, and so is parallel to the relative permittivity variation. This decay vector is perpendicular to this line, it's perpendicular to the fringes, and phi is as shown. Geometrically, the red dashed line bisects the angle between the two input beams. And this is equal to this here. The grating vector is perpendicular to this line, so we simply say phi is going to be pi over 2 plus this, which is given by this formula here. Again, I'm very sorry about this. I tried to switch it off, but it doesn't seem to want to let me. Okay. Going back to the solutions of the differential equations, we substitute the expressions for R, Z, and S of Z in. We get our two simultaneous equations, and we can solve for these gamma, which appear in the exponentials. And we have this form here, plus and minus. We have two of them. And the gamma variables are defined independent of the boundary conditions, and so are independent of the geometry of the grating. Therefore, these definitions of gamma I and gamma 1 and gamma 2 will be used for both reflection and transmission geometry gratings. We just apply different boundary conditions. The boundary conditions for the transmission case, as we said, R at 0 is 1 and S of 0 is 1. Since the diffracted beam is forward traveling, sigma of Z is greater than 0 and CS is greater than 0. And we apply the boundary conditions, and the complex functions are derived for the variations. Would advise those interested to actually carry out this calculation. In the end, however, we are primarily interested in the sizes of the beams leaving the grating and the diffraction efficiency of the grating to get these values. We need R of D and S of D. So we want to find these two values, what's transmitted and what's diffracted. And if we go away, we can find out that we get expressions which look like this, where we now have this dephasing parameter, and now we have this capital phi term here, a cosine and a sine. And the S of D is given by this, where we only have a sine of this phi. And this nu is kappa D over the square root of CRCS. So previously, we would have had the cosine of both of these would have been cosine theta. So we would simply have had a cosine theta here. In this case, the dephasing parameter, we have the cosine, the CS, associated with the diffracted beam, not with the replay beam. And our phi here is going to be the square root of the grating strength squared plus the dephasing parameter, the upright parameter squared. Okay, so it's very similar to the unslanted case, but we have to be careful about these angles and where these angles come from in this unslanted case. If we have nu is equal to a term that looks something like this, so we have a diffraction efficiency which is equal to 1, yeah, we're going to have an on Bragg response which is 1, and then as we vary our angle, we're going to decrease, we're going to lose the diffraction efficiency. And we see that we have the same sort of behavior here, depending on the diffraction efficiency we start with, depending on which side of the growth curve, whether we're on the rising side of the sinusoid, through the maximum to the reducing side. And as we tend to get, what tends to happen is that as we overmodulate, we get larger side lobes. We get the same types of characteristics as we go off Bragg with angle as with wavelength. In the case of transmission gratings, we tend to be very narrow, so we have very small variations in angle, produce very large changes in our diffraction efficiency. Whereas we can have large changes in the wavelength and we still remain close to on Bragg, we still retain high diffraction efficiency. So if we send light through a transmission grating, we tend to see a rainbow, a very clear, distinct rainbow. On the other stand, for reflection gratings, we tend to not be very angularly selective, but we do tend to be very wavelength selective. So if we shine white light onto a reflection grating, we tend to get only one color reflected. This would be a typical type of actual physical off Bragg response that we would see. And what we note here is that there's This is probably more true of material like silver halide, but what we note here is that we tend to have some sort of a variation which is due to scatter or loss in the graininess of the material or loss. We have a very clear on Bragg diffraction efficiency, the dashed line, and we can see our transmitted beam drops down on Bragg. But this curve, this variation here is due to the material characteristics. And what one might often do is one would take this region here and you'd normalize with respect to this background variation. So for example, you could take a material and you could expose it with a uniform beam, and then you do some sort of an angular scan on it to find out what happens to the transmitted beam. And then you would normalize with respect to that. So you take out or remove all the effects due to, for example, Fresnel reflections or due to the scatter in the medium or absorption in the medium. And once you do that, you get something much, much closer to what Cognix has here. You have to be careful with your Fresnel reflection conditions, and I'll talk a little bit about that later. And you can zoom in, you can find your half height maximum efficiency, and you can find out where the first zeros are. If you've got a nice uniform grating, you'll get something very nice and smooth over here. And when you've got non-uniform gratings, you get distortion. And we're going to talk about non-uniform gratings. The diffraction efficiency, as we said now, previously we had these two obliquity factors, but for the unslanted case, the angles were equal. Now we've got to make sure that we retain the correct angle. So we have the CR here, the cosine theta down below, and we've got the magnitude of the CS up here on top. And we're going to have a case when we've got an input, which is 1, it's going to be given by this with this ratio between these two obliquity factors. And it turns out those are important. If we don't retain those and we don't use the correct form, we actually get worse results. And we can come down and we can look at the off-Bragg case, and it simplifies down to this grating strength divided by the phi, the square root of grating strength squared, plus your dephasing off-Bragg parameter, and the sine of the square root here of the sum of the two. And when our off-Bragg parameter is 0, this phi becomes equal to the grating strength, and we're back again to exactly what we had before, that a diffraction efficiency is the sine of the grating strength all squared. So eta is the diffraction efficiency as defined above, only tells the fraction of the power input into the grating in the z direction, which is coupled into the z direction of the power in the diffracted order. And many graphs presented in the literature show the diffraction efficiency of Bragg divided by the diffraction efficiency on Bragg. So it's a relative. And so they will plot graphs where they show gratings with different strengths, with different on Bragg diffraction efficiency because they've got different grating strengths, and they'll normalize them all to that. So it gives you a much clearer picture of what's happening in terms of the actual side lobe structure, that you normalize with respect to the actual strength of each individual grating. And we show that varying as a function of, for example, the dephasing parameter, the replay angle or the replay wavelength. And these curves are effectively normalized to the value on Bragg. And this is usually done so that the angular and wavelength filtering characteristics, so how quickly it rolls off and how large the side lobes are, can be seen clearly, and they can compare between the two. And this becomes particularly interesting when you overmodulate or when you've got non-uniform gratings. So the angular or wavelength filter characteristics of these gratings can be examined, and these filtering characteristics include the width, the bandwidth of the central lobe, the size of the side lobes of the off-Bragg transfer function, or the rate of roll-off of the curve. So all these characteristics we associate with filtering. It's of some considerable interest to us to examine these characteristics to see how the response of a grating varies as the recording and replay conditions vary. What we will develop are several rules of thumb, and upon making some approximations. So this is quite sort of general, just get a feeling for what's going on. Because although the formulas are relatively simple, in many cases, if you just can do something on the back of an envelope, it helps you. So let's just start by telling lambda 0 and theta 0 to be the wavelength and angle of incidence of an on-Bragg beam. And then define delta lambda and delta theta as deviations from the Bragg condition. And Cognix showed that using this definition of this dephasing parameter, the definition we gave, where lambda is the free space wavelength, to the first order, that dephasing parameter can be written as follows. So you simply substitute in, for everywhere you've got theta, you put theta 0 plus delta, and everywhere you got lambda, you put lambda plus delta. And so, you put lambda plus delta, lambda 0 plus delta. And if you do that and you expand it out, you can see that you're going to get a dephasing parameter, which is effectively given by this formula here, this perturbation. Okay, so this here is the small angle variation, small wavelength variation. That's what your dephasing parameter becomes. And of course, if these are 0, then this is equal to 0, and you're on Bragg, and your dephasing parameter is equal to 0. So it's interesting to note that certain amounts of delta theta and delta lambda produce the same amount of dephasing and can in fact cancel out one another. So we see here we have a minus sign. So we put a certain value here, we put a certain value here, we could in fact still have this equal to 0. So this comes back to the idea I told you that you can remain off Bragg even though you do not replay the grating with the recording wavelength and the recording angle. You can cause the two effects to cancel one another out. You can change your angle and change your wavelength and still stay on Bragg. They can cancel out to bring replay back on Bragg. The off-Bragg parameter can be written as the following form. So now we've just written the off-Bragg parameter here, and we've got the delta theta here. This will be the off-Bragg parameter as a function of delta theta, and this is the off-Bragg parameter as a function of delta lambda. So we see this linear variation. These are linear variations in terms of the other parameters in the device. Okay? And again, of course, as you move off Bragg, your CS or CR will vary. But again, you can build that in here, and you'll still see that this will be effectively a first order effect. So you can replace CS by CR, and you'll still have the same value here. You can go away and have a look at that. It's found numerically that the half power points are usually reached when the off-Bragg parameter is equal to 1.5. The advantage of using this off-Bragg parameter is it generalizes. It makes everything, for any grating, it sort of normalizes everything. So you don't worry about wavelength, you don't worry about angle, and in some ways you don't worry about the actual parameters in the grating. You've got a generic, it's effectively normalized off-Bragg parameter. And if you move off Bragg with a particular grating, independent of its strength, when you hit this zeta value, this off Bragg parameter 1.5, you're pretty much going to have reached the case when the diffraction efficiency divided by the on Bragg diffraction efficiency is equal to a half. It's a pretty good value. It's a good engineering result. It's also found that the larger this grating strength, the narrower the central lobe. So of course we have this, and on Bragg, the diffraction efficiency is going to be sine of this squared. So the narrower this is, if we look at our off-Bragg response, the higher the diffraction efficiency up until we reach a value of 1, then we get over modulation. But in general, the larger that is, the narrower the central lobe is going to be. However, a large grating strength also implies larger side lobes. As we make the grating strength larger, and as we go into and of course, that grating strength continues to get bigger. It's a function of kappa, and kappa is a function of the modulation. So as we expose longer and longer in these ideal conditions, our grating strength is going to increase. And what we find out is that we're going to basically get stronger and stronger side lobes. For an unslanted grating, when these two are equal to 0, phi is equal to pi over 2, we substitute this 1.5 value into the off-Bragg equation, and it gives us that this 2 times this delta theta, where you've got this half value when the zeta is equal to 1.5, is equal to the period of the grating divided by the thickness. So that's quite a nice little result. We can change by that angle and we reach the half value. And if we want to have a whole load of gratings together inside the same layer, that gives us a very nice rule of thumb to tell us how many of these gratings we can stack. Yeah, because we're going to want the diffraction efficiency, the off-Bragg responses to be separate enough so that, for example, we have only the half power point overlapping. It reminds you a little bit maybe of the the Rayleigh resolution limit, okay, where we've got the point response, and we can say, well, we can determine 2 points, we can separate 2 points as long as the maximum one overlies the first 0 of the other. In this case, we're talking about the half power points. We're actually putting these things lying closer on top of one another. Okay. And we have a similar expression we can get for the actual half power delta lambda, which gives us a cotime of theta times this period, the half power wavelength bandwidth. So I hope you can kind of see where this might be very useful as a very nice little rule of thumb. Okay. And as an engineer, I love this sort of stuff because it gives you nice little insights, quick ways to do calculations in your head. Okay, you still have to go away and check them using more rigorous analysis, but still it's a very nice way to just get a feeling for what's going on. Okay. Now this is straight out of Sims' book, and I've pilfered Sims' book here. Here's our grating strength. It's given by this formula here. And what we've actually got here is we've got 3 different gratings, and each one of those gratings has a different grating strength. So we've got this one here, which is the grating strength is pi over 4. And this one over here, it's 3 pi over 4. And the one in the middle is equal to pi over 2. So the pi over 2 one, this black one here, that has a diffraction efficiency which is equal to 1. And all of the others have diffraction efficiencies less than 1, but we've normalized it. We've taken their diffraction efficiencies on Bragg and we've divided the whole curve by the value on Bragg. And what that brings out very clearly is that as we get our grating strength and as the grating strength increases, so it increases from pi over 4 to pi over 2 to 3 pi over 4, so this will be an overmodulation case. So we've gone up to our maximum and now we're coming down the other side of the sine function. The side lobes get much bigger. We see also that as we increase the grating strength, the position of the first zero gets smaller. Yeah, we move in this direction. Okay, so we've got a zeta axis here, and here we see the first zero for the pi over 4 is here somewhere bigger than 3. And as we move in here, we've now reached a position where the first zero is at 2. We can also see that this normalized curves that for this value of a half, where this diffraction efficiency divided by the diffraction efficiency on Bragg is a half, we can see that all of these values here are not too far away from z is equal to 1.5. So a mathematician would go crazy here, but an engineer is quite happy to just say, oh yeah, they're all about 1.5. And then to use that value to do various calculations. It's a good rule of thumb. And always a good rule of thumb is usually one which gives you a calculation which is a worst case. Okay, so it gives you a worst case result. So I hope everybody can see what I'm doing here. And so the important point here is I've got my diffraction efficiency, the actual diffraction efficiency for these different grating strengths divided by the diffraction efficiency on Bragg for those grating strengths. And what we've enhanced here is we've actually enhanced the actual size of the side lobes. So we can see the side lobes, relatively speaking, are getting much worse. Okay, if we include the direction change across the input boundary, so now we're talking about refraction across the boundary. We've got a change in the angle. Very good. So we have an input angle here, and then we've got to cross this boundary into this medium, which has a different average index. So for example, from air into the actual grating. What we're going to see is that, of course, this would have happened during recording. So if this is the on-Bragg angle outside, this is the on-Bragg angle inside, because this would be the beam angle when we actually did the exposure. But we can see also that in this case, we go from low index to high index. Changes in the angle outside are going to produce changes in the angle inside, but the changes inside are going to be smaller because we're going from a low index to a high index medium. And we've got to apply Snell's law. So we're assuming here this is air, so it has a refractive index approximately equal to 1. And so we got sine of theta prime is going to be n, the average index inside the hologram, times the sine of the angle inside the hologram. And we've got to be very clear about this. Remember our model, we said it was as though we had a volume material that filled all space. So when we talk about, and when we've talked about so far, the Bragg angle, the angle on Bragg, we've been talking about the angle inside the layer, inside the holographic material. So we've been talking about theta here. But of course, in the real world, we're going to have to allow for the fact that we've got a theta prime outside. And so we've got to allow for this conversion between a delta theta outside and a delta theta inside via the Snell's law. And so again, very nice little expression, sine of theta prime plus delta theta prime is equal to n times sine of theta plus delta theta. And the fact that this sine of delta theta, remember delta theta is very small. So sine of a small angle is the angle, and we just would stress down this is in radians. So we have to be careful that this is in radians, not degrees. Because of course we could have 10 degrees here, but sine of 10 degrees is not 10. Okay, so this is radians. And cosine of delta theta is going to be equal to 1. This gives that this is going to be equal to this, and therefore we have a conversion between the angle outside and the angle inside. So deviations in the angle outside to deviations of the angle inside. And we have this delta theta half inside is equal to this. And so we have a relationship between the delta theta prime half outside and what goes on inside. We have an expression. And again, we see it's related to, it's proportional to here, the period divided by d. But we have here this twice the zeta at pi. And again, we can use here 1.5, for example, here, if we've got the zeta half value. And we've got n times cosine theta over cosine theta prime. These are all little corrective factors. It's worth emphasizing the point made about diffraction efficiency and power conservation. Okay, so we have to be a little bit careful here, especially when we go off Bragg. we've stated that our model is for planar gratings, and these gratings are infinite in the x direction, and they're infinite in the y direction as well. We've got power transfer only in the z direction. They're infinite in the y direction, are simply independent of the y direction. We don't have anything happening in the y direction. In the z direction, the grating is finite, but upon ignoring the second derivatives, as we have stated, the grating effectively fills all space. Okay? Although the x variable does appear in our analysis, it can be seen from the differential equations coupling as only dependent on the grating thickness. The coupling is only dependent on z, it's not dependent on x. We know nothing about any variations in the x direction. Now, I'm emphasizing this in relation to Cognix theory, because often you end up in these sort of funny discussions about particular applications, but you got to be very, very clear. So if you've got sort of a grating and you're hoping to use the transmission function of the grating and the reflection function of the grating in some way, or mixing them in some way, the analysis, Cognix analysis is limited. You've got to be careful. In the x direction, since the grating is infinite in this direction, any power traveling in the plus x direction is cancelled out by an equal amount of traveling in the minus x direction, and therefore the coupled wave method tells us nothing about power traveling parallel to the boundary. The model is essentially pseudo two-dimensional. Okay, it's pseudo two-dimensional. Power is implicitly conserved. Okay, it's built into the differential equations that govern this and our assumptions that power is conserved in the coupled wave analysis. And we can show this very simply. We take the actual equations we've got, the differential equations, and we take their complex conjugates. Yeah, so we take our this is equal to 0, and we multiply this by R complex conjugate. And this is our second equation, and we multiply that by S complex conjugate. So we've just done that. We've got the conjugates, we have a total of 4 equations, okay? And we add all of these together. So we add all this to its complex conjugate, this to its complex conjugate, yeah? And if we do that, we're going to end up with an expression which tells you that the rate of change with respect to z of this term, this expression, yeah, is going to be equal to 0. And this equation represents the balance of power. It represents the balance of power traveling in the transmitted and diffracted directions. Yeah, the diffracted waves move approximately in the rho and sigma directions. Therefore, the total power moving in the z direction is given by this. That's the total power. In a lossless grating, this is equal to the complex conjugate. This is equal to its complex conjugate. Remember, if we've got lossy gratings, our kappa has got a coupling constant. There's a coupling constant associated with the absorption grating, but now for a real grating, that's going to be real valued, and the dephasing parameter is going to be real value. And the total power in the system is a constant. The derivative with respect to z of that term is equal to 0. So what we've done today is we've encouraged people to read and work through Cognix and to look at SIMS. We've revised the early work with Cognix, talking about slanted gratings, and we've emphasized this idea of on-brag, off-brag, and these nice little rules. Worked through Cognix, so repeated ourselves here, but just to get people used to what's going on, the mechanism of what's going on. For slanted transmissions, and we've talked a little bit about reflections, we've introduced obliquity factors. Yeah, we examined the geometrical origins of the slant, the slant angle, and we derived the R and D and the S of D. We've looked at the effects of varying theta and lambda, moving off-brag, and we've looked at the off-brag response, especially the half-power bandwidth, which is particularly useful when you start talking about putting in multiple gratings, for example, and this would also apply to things like holographic data storage, when you're trying to store gratings page-wise, for example. And they're good first-order rules of thumb. We developed some rules of thumb to find the bandwidth. We've examined the effect of changing the grating strength on the off-brag transfer function, and we've examined the effects of index mismatch between the media, and we've got a corrective term there. And we've examined power conservation in the thickness direction. Okay, so we did quite a bit now in that expression. A lot of it was repetition of stuff we've done before, but we tried to flesh it out and give you the words associated with it, and hopefully now this will help you and mean something to you going forward. Okay. Okay. Now, is everybody okay with that? We can take a little pause now. We're about at the 45-minute page. Has anybody got any questions about that? I'm hoping it should be, straightforward, based on the amount of time and energy we spent on the first stuff and going through it very nice and slowly and talking about Cognix theory. I'm hoping now that it's okay that I go a little bit quicker here, and that I've tried to emphasize the most important points, I think, and the most useful ideas, and to show you why Cognix is so useful, that people can use this to do a mountain of different types of ideas. Okay? So are there any questions on that? Okay, well, if there's no questions, I'll move on to the next one. And the way I've broken these lectures up, it's a little bit arbitrary. You know, I've given talks like this to various groups before, and in some cases they want certain things emphasized. So these do follow in sequence, but as I said to you, for example, this idea of the half power bandwidth, some people are very interested in that, and they want to look at that in great detail. And for you guys, I think it's kind of a very nice rule of thumb, and it sort of indicates that power of this Cognix idea, that you can extract out these very simple and clear little ideas. Now, so far, we've pretty much concentrated on transmission gratings, and I'm going to spend a little bit more time looking at reflection gratings, phase gratings, using Cognix K-vector closure method. So first order two wave. I'm going to compare the responses of reflection and transmission gratings on and off Bragg. So I've already mentioned some of these. I prepared the ground here, hopefully, for you guys, so I'm not taking too big of a leap. But I think it's worthwhile treating the reflection gratings by themselves. Again, some people might spend most of their life talking about reflection gratings, and some people might spend most of their life talking about transmission gratings. But I think it's good to treat them both with sort of like equal respect. And I think for ITMO people too, I think you guys are going to be very interested because, of course, of the famous Denisuk and his work with these reflection gratings. Okay, and as I said to you, the fact that we're coming up on the 60th anniversary of his work. So we compare the response to reflection and transmission gratings, and we're going to examine the case of TM polarization. So far, we've always, and I'll give you a couple of figures where I showed you this, but so far, we've always talked about the place where the E field was parallel to the actual boundary, and it was parallel to the actual fringe pattern, okay? So we had the H field would have been perpendicular to the direction of propagation and perpendicular to the E field. And so if we actually rotate the replay conditions. So if we don't, so we typically expose using the TE polarization because we get our maximum fringe visibility in that case. And therefore we're going to get the maximum reaction from the material. Now again, I'm talking about standard materials. There are materials which have particular polarization properties. And there are some advantages actually to recording with circular polarization. So situations where, for example, you're not sure what polarization you're going to be replaying with. And there are applications where polarization becomes important. So for example, I'll maybe show you an example later, some work I did previously on shuffle networks, where you had an array of holograms and you were coupling from an array 2x2, a two-dimensional array to another two-dimensional array. And therefore, if you had linear polarization out, you could get your maximum diffraction efficiency by effectively rotating the grating with respect to the input beam. We'll talk a little bit about that, just to show you that these things are not just theory. Okay, might come across as theory, but just as the small angle approximation becomes quite important if you're trying to store a lot of different gratings in a medium, actual polarization effects become very, very important if you're trying to build things like shuffle networks. So this isn't just fun if you want. It might be fun for me, but it's actually things that are useful to engineers. So we're going to examine the case when we've got a different polarizations incident. I'm going to give you a sort of a short introduction to that. And then the next day, I'm going to talk about that in a little bit more detail. So again, I sort of promised you that I'm going to try and do something a little bit about every day about something we've done in our group. This was a project where we built a mask, as you can see here. And the mask you can see is a blue light. And basically, we can put that on the horses and we can trick the horse's body into thinking, for example, it's spring. And by tricking the body of the horse, the mare, into thinking it's spring, we can actually control when the horse is pregnant. Hello? Hello?
Una pregunta, ¿sabes si Inma te envió ayer un presupuesto de material?
Hello? Is somebody talking? Is there a question? Is there a question?
La empresa es Tecnoquín, es cosas de laboratorio.
Hello? Is Marta talking? Hello? We can hear you talking. Okay? So anyways, we can control the fertility of the mares, and so we can increase the number of young horses or foals that are born. And we've also put lighting into stables. And the horse industry is a big thing in Ireland. And this actually saves people a lot of time and energy and makes them money. So we've had a very successful work in this area. And it's fueled, if you like, my interest in broadband light sources and bio-optimized lighting, where you choose your lighting so as to produce some biological effect, whether it's wakefulness or fertility. I always tease my students and say that I started to do this project work because I wanted to reduce the sexual activity of my students, okay, and it failed. So we decided then to control or increase the sexual activity of horses. Okay, now here we have again, and I'm going to emphasize these things over and over again just so you get used to this. And I know it might be annoying, but I think it's just to get you more and more used to this idea of representations and descriptions. Here we have a recording, and here we have the replay or reconstruction of this slanted transmission grating. And we have specifically laid out here the conditions, the boundary conditions in that case, and we want to know S of D and R of D. And in the reflection case, we have our two beams coming from opposite sides, and we end up with slanted fringes like this. And again, if we replay, we now have a diffracted beam and we have a transmitted beam. And in this case, these are our boundary conditions. This is 1, this is what we want to find out. This is equal to R at D, and S at D is equal to 0. We have nothing coming out here because it's a reflection geometry. The Zenizuk or Lippmann type reflection geometry is very much this unslanted, and it can be produced, for example, by exposing. You can get a nice unslanted dielectric mirror by simply illuminating with a single beam and placing a mirror behind the actual holographic emulsion. And then you're going to get a specularly reflected beam from the emulsion, which will produce a standing wave pattern with fringes as shown, and that will produce our dielectric mirror. And we can also produce, using slanted reflection gratings, we can produce these off-axis mirrors. So if we get a large percentage of the power reflected, we're actually got this reflection, effectively a reflection. We put power in, we get everything reflected, but it's not specular reflection. We don't have this symmetrical situation where the angle of reflection is equal to the angle of incidence, okay? So these are off-axis mirrors, and things like that are used for things like head-up displays. And I mentioned Lippmann here, and again, I would send you off to go and read a little bit about Gabriel Lippmann. It's pretty cool stuff. Okay, so reflection geometry gratings. In all of the examples discussed so far in detail, certainly in detail, we have concentrated on the case when all the significant diffracted orders are traveling in the forward direction. And this grating geometry is called transmission. And there also exists a geometry which we call reflection, in which significant diffraction orders are traveling backwards or in the reflection direction. And this is called reflection geometry. And in the first lecture, we presented a set of EVA diagrams for the geometry shown both on and off axis replay for angle and wavelength variation. So we've sort of met these, and I've talked a little bit about them. And again, I just want you to be very good if you just get used to the idea of drawing these things and the geometries and the way we describe them and how we talk about them. In the figures, we present the usual XZ representation, where Z is the direction where we get the coupling, the thickness direction of the two geometries in the transmission case. The diffracted order travels left to right and has value at 0 at Z is equal to 0. So again, just another thing I just noticed, if you look at your textbooks, is that light always tends to travel from the left to the right. It's quite miraculous. But if you go to 99% of textbooks and you look at drawings of optical systems, the light always starts over on the left and it travels to the right. And it saves a lot of thinking for the reader. So we have S at 0 is 0. In the reflection case, the dielectric order travels from right to left, okay? And so the value is 0 at the far side. So we have S at D is 0. In both cases, R at 0 is assumed equal to 1. So transmission and reflection. And in the second lecture, we derived the differential equations for a slanted grating and solved these equations for the transmission geometry. Differential equations and the form of their solution are given on the page 9 above in lecture 2. And at that time, then calculated these the gamma 1 and the gamma 2, which appear in the expressions for S of Z and R of Z. And I pointed out that these values are the same form independent of the boundary conditions. So you set up the form of solutions with these particular eigenvalues, and then you apply boundary conditions. So the differential equations and the generic solution of the differential equations are the same for the transmission case and the reflection case under Cognix. What changes is the boundary conditions, okay? And of course, physically, what's changed is actually the orientation of the K vector. So physically, we have differences in the K vectors themselves, but mathematically, we simply going to apply different boundary conditions to the same form. This similarity for both geometries must of course be true for a reflection grating is simply a slanted grating with a large slant angle. So we can just think of starting off with a transmission grating and introducing slant. And if you start off with a transmission grating and you rotate the actual grating by 90 degrees, so that instead of the fringes being perpendicular to the boundary, they're parallel, you've gone all the way around the evil diagram. Your K vector no longer points in the X direction, it now points completely in the Z direction. So you can think of reflection gratings as slanted transmission gratings or vice versa. And this grating is a large slant angle which has been replayed in a particular way. And just to interject here that you can in fact start off with something and replay at a particular angle and it acts like a transmission grating, and if you change the angle of replay it will start to act like a reflection grating. You can go away and draw your evil diagram and see that this is the case. Of course, all the variables in these gammas will change for each grating model. So the capital K, the grating vector changes, etc. And of course, the obliquity angles are going to change. Certainly, they'll change their sign. But the only change dependent on the geometry will be the fact that for a transmission grating, the obliquity factors of the refracted order, the CS, will be greater than 0. And for a reflection grating, the obliquity factor CS is going to be less than 0. It's going to be negative. Only upon applying the boundary conditions, however, do we separate the two regimes and do we allow us to calculate the diffraction efficiencies. We've already analyzed the transmission case, so proceeding in the same way for the reflection case, we now write down our boundary conditions and we write down the resulting formula. This here is for R0 is equal to 1, which implies R1 plus R2 is equal to 1. And S of D is equal to 0 implies that this term here is equal to 0. So two simultaneous equations. Now applying the 4 equations found by substitution, the expressions for R and Z into the differential equation, we've got 2 differential equations under this constraint. So we can use these to remove, for example, eliminate an R1 or an R2 or an S1 or an S2. And then we substitute that into our 2 coupled equations, and then we have 2 simultaneous equations. It can be found. So we recall that our expansion for R of Z is that, and for S of Z is this. And we substitute in, and we get these formulas in our coupled equations. So here's R1, R2, S1, S2 into the coupled equations. And here we have the dephasing parameter, and we get S1, S2. So 4 equations. This is page 11, lecture 2. And we have this defined in this term. Here's our dephasing parameter, the dephasing parameter and coupling constant, and the various obliquity factors. And from the boundary conditions for the reflection case, these two, we get that R1 is equal to 1 minus R2, and S1 is equal to S2 e to the power of gamma 1 minus gamma 2 times D. And that's going to give us the following expressions. So now we have 2 simultaneous equations. We substituted in. We got 2 simultaneous equations, and we got 2 unknowns. We got R2 is unknown and S2 is an unknown. And so we can go away and we can solve for these things. And we can find out that R2 is given by this expression. And we can go away then and derive R1. And then we have expressions for, we can find S2 and S1, etc. And so we can go away and we can find out these expressions for the reflection geometry case, for R at D, so the transmitted beam on the far side, and for S of 0, the reflected beam on the input side. And we note here that we have these hyperbolic cosh and hyperbolic sine here. For the transmission grating, these were sines and cosines, but now we have these hyperbolic cosh and sine, and we've got a hyperbolic cotangent. Okay. Again, we have an expression for the grating strength. It's exactly the same form for the off-Bragg parameter in terms of the dephasing parameter, and our phi is now equal to the grating strength minus this off-Bragg parameter. But each one of these individual things here, they're going to be different. The actual values are going to be different, okay, because we have a different geometry. First, let us examine the case of Bragg incidence. So if we go to Bragg incidence, the off-Bragg parameter is 0. The phi here is going to be equal to nu, the grating strength, and R of D is equal to this arc or inverse cotangent of the grating strength. And sine the diffracted beam is going to be equal to the scale factor, the square root of the ratio of the obliquity factors, times the hyperbolic tangent. And we can see that the diffraction efficiency on Bragg, which is this R0 times R star, the complex conjugate, is 1. That's what we put in. The diffracted efficiency obliquity factors. This by its complex conjugate gives us this hyperbolic tangent of nu. And as nu goes to infinity, the diffraction efficiency goes to 1. So as we increase so this again is different now from before we had a diffraction efficiency which was sine squared. So as we increase the grating strength, we would increase our diffraction efficiency up to a value of 1. And if we increased our grating strength further, we would overmodulate and our diffraction efficiency would decrease. But now we've got a diffraction efficiency for the reflection geometry, which is the hyperbolic tangent. And the hyperbolic tangent, as you increase the grating strength, it gets closer and closer to 1, but it never quite gets to a value of 1. It only gets there when the grating strength is infinite. So we've actually got an infinite thickness, or we've got or infinite modulation. And power conserved is given by this. So again, we have our input power, and we have this factor here in front of these, and that's going to give us sec squared of the grating strength plus tan squared of the grating strength is going to be equal to 1. And if we go and actually do out the plot of these things as functions of depth, so this is z is 0, and at z is equal to 0, or 0 is equal to 1, the blue line, and the diffraction value is equal to its maximum value. And as we go forward with R, we see the amount of power in R decreases as we go forward because it's being coupled into the backward propagating diffracted beam, which is increasing. So R of Z decays in the plus Z direction, and S of Z increases in the reducing Z direction. And if we look at our curves for our diffraction efficiency, we get something which looks like this. Here's our input beam. And as we increase the strength of the grating, we increase the modulation or we increase the thickness, what's going to happen is the transmitted light is going to decrease, get weaker and weaker. And as we make the grating stronger, the diffracted light is going to get stronger and stronger. Okay? So these are the growth curve associated with reflection gratings. Proof that power is conserved, so that the sum of the red and the blue here always give you 1, that power is conserved, was based on the differential equations which govern all the geometries. We've already given that proof, and the proof we've given is true for transmission and for reflection gratings. It's simply based on the actual form of the diffraction equation, differential equations. On Bragg, the variations with the grating strength of the efficiencies are as follows. We've seen the figure before. When we've got a grating strength of 1.8, we get a diffraction on Bragg diffraction efficiency of 90%. And for a grating strength of 3, we get a diffraction efficiency of 99%. Again, this grating strength depends on it's linearly varying with the modulation and with the thickness. We recall that for the transmission case, when the grating strength is pi over 2, we're going to get 100% efficiency for the transmission case. Thus, theoretically, and practically, it is necessary to use a larger grating strength, so a larger modulation and thickness, to get a comparable efficiency in the reflection case than in the transmission case. Okay. And again, this here is a linear function of these two things. It's kappa times d divided by the square root of CSCR, or the magnitude of CSCR in the reflection case. Next, we must look at the off-Bragg characteristics of reflection gratings in the same way that we examine them for transmission gratings. Okay, so down here. So again, what do? Well, we plot out the diffraction efficiency for that particular grating strength divided by its diffraction efficiency on Bragg. The replay characteristics of reflection gratings are similar in many ways to those of transmission gratings. And in general, there are 2 Bragg angles, except unlike the transmission case, the 2 recording waves are counter-propagating. So they're incident from the opposite sides through the grating, through the medium. And again, if you think about your simple unslanted reflection grating, the mirror case, you can put the beam in coming from the top down and you get reflection in the diffraction direction, or you could put the beam back up the input beam from the opposite side, and again, you're going to get reflection, specular reflection. So again, here's our curves, and what we have here is we've got different grating strengths. We've got mu now, and we've got pi over 4, we got pi over 2, and we got 3 pi over 4, just as we had for the transmission case. And for the red one, this will give us a reflection on Bragg of 43%. In this case, we get a reflection on Bragg, which is 84%. And in this case, we get a reflection on Bragg, which is 96%. Those gratings would give us different. And in all cases, we've divided by the actual value by the diffraction efficiency on Bragg. Okay? And again, here's our values for these cases, these individual cases. And in terms of this figure up here, what we're basically saying is, okay, we take a value here where we've got 40-something% in our diffraction efficiency. So this would be here for one of them. The next one is 80. So it's out here somewhere. And the next one is over here, something at 90. Okay, on that growth curve. So we could imagine we grow the grating, we do an angle scan, we grow the grating further, we do an angle scan, and we grow the grating even further and we do an angle scan. And that's what we would get here. Okay. And again, what do we see? Well, as we increase the diffraction efficiency, as we increase nu, the point, the first 0 point moves outwards. Okay. And furthermore, as we increase the on-Bragg diffraction efficiency, the relative size of the first lobe increases. The first lobe increases. We have this nice characteristic, though, that as we increase the grating strength, we're getting something here which looks more and more like a very nice rectangular filter. So we get this variation here, this rapid roll-off of the filtering effect, a very rapid roll-off. Okay, so we got a filter, it's very linear over this region if we're varying wavelength, for example, and then we get this very rapid roll-off over here. And in fact, we can see that if we increase this eta more and more and more, we're going to get a bigger and bigger flatter region. Okay, so that's usually a nice characteristic for a filter, that it has a good central flat region and then a very rapid roll-off. It's not nice if we then have a very strong side lobe over here. And if we look at our off-Bragg response, again, this is normalized. Here's our transmitted beam. We get this oscillation effect. Here's our diffracted beam, this dashed line here. And we have our half wave power, the lambda Bragg plus and minus delta lambda over half, or plus and minus delta theta over half. And here we have our off-Bragg parameter. Yeah, we can plot it as functions of wavelength. We can convert the wavelength into a dephasing parameter or an off-Bragg parameter. So many different types of representation. And we can look at the point when we fall into half of the intensity on Bragg. And we see here the on-Bragg intensity here isn't going to 1. And the transmitted beam doesn't go to 1 because we've got a reflection grating. But if we add the two together, we get 1. And we can compare this to the case we had before for the transmission case. And as I said, in general, when we talk about reflection gratings, we're going to be interested in the off-Bragg wavelength variation, whereas for transmission gratings, we're interested with the selectivity associated with angle variation, because both of them are more selective in the two different parameters. So we got a case, we got D, the thickness is 10 micron, which would be a very thin layer. Wavelength is about half a micron, which is pretty much the middle of the visible. Recording angles are theta B1 is 15 degrees and theta B2 is 165 degrees. Again, whatever way you describe your angles, as long as it's consistent. And the replay is at 15 degrees fixed. So what do we have? There is only one case. In general, the shape of the off-Bragg curves near on-Bragg is flatter for reflection gratings, so I pointed that out to you, than for transmission gratings, as with comparable parameters. So again, you can only compare like with like. So similar thicknesses, similar grating strengths, or similar diffraction efficiencies. In general, the wavelength selectivity of reflection gratings is greater than for comparable transmission gratings, so they let through a narrower band of wavelengths. They diffract the light over a narrow band of wavelengths. And you can just check this out. We've already talked about several ways to examine the off-Bragg response of gratings, so the diffraction efficiency, the half power bandwidth, and the side lobe side. Let us now introduce another test, the position of the first 0. Okay, so we talked about the half power. We can also look at the position of the first 0. And again, we can use this to characterize the information, or the way we can store separate different gratings. Okay, and then use this to compare the relative change in wavelength necessary for both grating geometries to produce such a 0. So first, let us return to the transmission geometry grating. CS is positive. We've got two beams coming in from the same size, and our diffraction order is on the opposite side to the input beam. So we choose the case when we have the grating strength is pi/2, which means we have, for the transmission case, 100% diffraction efficiency. And we assume this is almost constant as we move off Bragg. So we have a diffraction efficiency on Bragg. Now we move off Bragg. And what's going to happen? Well, eventually we're going to reach a point where we have 0 diffraction efficiency, and that would correspond to the first null in our grating case. Now again, we're assuming perfectly uniform gratings. And this sort of ties in with some of the things we talked about before about scattering and interference. We only get this perfect first zero if all the light scattered from the different parts of the grating, when we add them together for that particular angular replay of that particular wavelength, completely destructively interfere and we get nothing diffracted, no output diffracted power. So we go to the first null, the first zero in the side lobe structure, and we can write that in that case, we're going to have this sign of the square root of grating strength plus the off-Bragg parameter is equal to 0, and we write this off-Bragg parameter here as zeta sub 0, okay? And what we find out is that zeta sub 0, therefore, is going to be equal to plus or minus the square root of pi squared minus the grating strength squared, yeah? And if we've taken a value of grating strength, which is pi over 2, we're basically going to get a zeta 0 value, which is equal to plus and minus the square root of 3 pi divided by 2. So we have an expression which tells us that if we move this much off Bragg for a 100% diffraction efficiency grating, that off Bragg value is going, that's where the 0 is. This is the first such case. And we know that this off Bragg parameter is given by this the dephasing parameter, and we call it the dephasing parameter 0 times the thickness divided by 2 times this cosine of the obliquity. Okay, and this is for the diffraction order, the -1 order. And we can put in here, we can rewrite this in terms of a delta lambda 0. So we assume that this dephasing parameter here is only due to a change in wavelength. And so we can rewrite this in terms of this wavelength. And of course, we still have D and we still have CS, but we end up with these other factors here based on our calculations, our definitions of the off-Bragg, the dephasing parameter. Remember, we said it was equal to the sigma minus the sigma squared minus beta squared divided by beta, 2 beta. And so we have this expression here in terms of the fundamental values, this sine of theta b divided by cs, d over the period, again, delta lambda 0 over lambda. So it's like a fractional variation. And for the unslanted case, just off Bragg, yeah, this is equal to this. This is the first 0 point for the unslanted transmission grating. So we have a non-Bragg case. We've got the variation that we have to use, and that's going to be equal to that, defined in terms of the period and the thickness of the grating and the tan of the theta angle. So again, hopefully you can see why this is very handy. Yeah, we can come up with these nice little expressions, give us 4 first order estimates of where the half power bandwidth is, of where the first 0 is, and this has consequences for the use and application of these devices. Now for reflection grating, the situation is slightly complicated by the hyperbolic functions. So up here, we had this sine is equal to 0, and so we had a very nice conversion between sine and this, and we could be very happy using something like that. Now we've gone from sine to hyperbolic sine, and hyperbolic cosine, etc. In this case, we want this diffraction efficiency equal to 0, okay? And we know what that's going to happen when this, yeah, this is the power -1, okay? When that's equal to 0, yeah? Note, if the zeta is equal to nu, we get this function, which is 0 divided by 0. And in general, we try to avoid things like that. I know that 0 divided by 0, we can define as being equal to 1. But often what happens in the real life is you've got to be very careful, because as things get very small, they're not necessarily exactly equal to 1, and you can have all sorts of problems. But we imply that this here is going to be equal to this. And if zeta is greater than that, we must use the hyperbolic sine of z is equal to this expression. So this is a standard converting from this hyperbolic to this trigonometric. So sine of j times y is equal to minus j sine minus y. And from the equation for eta, we see that eta is not equal to 0 when nu squared is equal to zeta squared. If nu is equal to pi over 2, then as before, we're going to get an expression which looks like this. So again, I'd ask you to go away and think about what I'm saying here. I'm giving you all the mathematical steps here, just trying to be very, very clear about what goes on. For the case of a symmetric reflection grating, so an unslanted case when the fringes are parallel to the boundary, we get the following, that zeta 0 is equal to this here, plus or minus the square root of 5 over 2 times pi. And once again, assuming that the grating strength changes little as we move off Bragg, and that cosine theta b is equal to cs, we get the following, that the delta lambda 0 over lambda is equal to root 5(2) period divided by thickness, which is pretty much approximately equal to the period divided by thickness. So the first 0 point for an unslanted reflection grating. And we can now go away and we can compare the expressions for the two. And what we see is that this ratio, yeah, to the first null for the reflection grating is smaller than the same ratio for a grating of equivalent strength in the transmission case. Okay? And that's true in general for smaller angles. In general, reflection gratings are more wavelength selective than transmission gratings. They are often used as filtering elements. So a fiber Bragg grating where you've got a long stretch of weak periodicity along the grating is a reflection grating. It's a wavelength selective reflection grating, can be used as part of drop ads and optical fiber networks. And the maths for it are pretty much exactly the same. Optical fibers and television. Once again, it must be emphasized. So, and of course, these passive type of selective elements are very useful for things like dense wavelength division multiplexing networks. Once again, it must be emphasized that the above expressions are only rules of thumb. They can be used to get a feeling for what's happening or in rough design work, but they're not always exactly true. So you've always got to be a bit wary of any rule of thumb, okay? There's generally some good truth behind them, and as long as they're worst case analysis, they'll give you a feeling as to whether or not something can be done. And then how well it can be done is a very, very different idea. And even with these rules of thumbs, if they say it can't be done or if it's marginal, you've always got to go away and do the actual calculation to find out. We have seen that we can change the wavelength of the incident light upon a grating, and the reflection geometry is more selective than the transmission geometry. So the amount of light diffracted by a transmission grating is greater than that diffracted by a reflection grating with comparable parameters. We've talked about this. Off Bragg by the same amount. Okay, so we've talked about these general characteristics. What happens when we compare the angular selectivity of both types of grating? So again, we have our dephasing parameter given as this form here. So instead of being a function of wavelength, it's a function of replay angle. And we compare the cases of an unslanted transmission grating with 100% diffraction efficiency and a grating of pi over 2, and a conformal phi is equal to 0 case. So this is when the fringes are parallel to the boundary. So again, this is language. Yeah, you can have an unslanted reflection grating. Yeah, and the conformal, a dielectric mirror, unslanted dielectric, an on-axis mirror. Reflection grating where theta r, magnitude of theta r is equal to magnitude of theta sub r in these cases. So here's our unslanted transmission case. Our k here is parallel to the x-axis. We're replaying it on Bragg with the rho, and here's a diffracted beam. And here's our unslanted reflection grating, our conformal, where our k now here is perpendicular to the x direction. It's parallel to z, and we have our replay, and we have a diffracted beam. And again, I want you to just get used to doing this over and over on the basis that you're just going to get used to it and you're going to be familiar with it, and you can go away and draw these things yourselves. Okay? As I said, this is hopefully I'm showing you why this is quite important and useful. This implies that the first null, as we move off axis for the transmission case, will once again occur at zeta 0 is equal to root 3 over 2 pi. And for the reflection geometry case, it's going to happen at root 5 over 2 pi. So that's not going to change from the wavelength case. This is simply because we've described them in terms of this off-Bragg parameter, which is generic. Recalling that the off-Bragg parameter is given by this, dephasing parameter times d over twice cs, we get for the two cases that this variation, this rate of change, okay, of the sorry, excuse me. This is for the transmission case, and this is for the reflection case, yeah. And this is d for the transmission case, and the period for the transmission case, and d for the reflection case, and d for the transmission, the reflection case. That pi over cs times this cosine theta is equal to this is equal to the off-Bragg parameter transmission case, off-Bragg parameter reflection case. The first zeros when the eta is equal to 0. Where we have assumed we can move off Bragg with only a small change of the input angle. So we're pretty much assuming a priori that we have relatively thick gratings or relatively strong modulation. We know that for the symmetric cases, this is equal to this. This is equal to magnitude. This is just absolute value because of the sign change going from transmission to reflection. And this is what we've shown up here. So these angles here. See, we've got theta, 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 and theta. So we've got this very nice symmetric situation. And we assume that we've actually chosen these two things, that in fact we've got these two things equal, or approximately equal. So the thickness of the transmission divided by the period of transmission is equal to the thickness of the reflection divided by the period in the reflection. In that case, we've got that this ratio between the two is given by this formula here. This is the tan of theta b. So the deviations we must make in the angle in the transmission case divided by the deviation we must make in the reflection case, okay, to move the same amount off Bragg for this symmetric case where these are true, is given by this. And what we see here is that as the theta b increases, this tangent is going to increase, okay? See, from this we see that the reflection angle, the transmission angle divided by the reflection angle, these deviations are less than 1. So we have to move more off Bragg, yeah, in this, so this angle is bigger than this angle. So we have to move more off Bragg in the reflection case by angle than we do in the transmission case in order to end up with the same variation, the same amount, moving the same amount off Bragg. And in theta is less than this for up to about 50 degrees. And again, this will be radians. We note that all of the angles used above are inside the grating, and that in general, as we talked previously, yeah, in general, reflection gratings are more wavelength selective and less angularly selective for common recording geometries. The problem is that if you go to very, very big angles, you're typically going to have large Fresnel reflections from the boundaries. And that means that makes it harder to actually get power inside to expose the material, and harder to get light inside to replay. It's not impossible, it's just more difficult. So for example, people do things like they put holographic emulsions or plates inside tanks of liquid, okay? And then they expose through the liquid, so the index match all the way around, and you can expose at very large angles from outside the tank, okay? Or they put prisms on top of layers to record and replay it for high angles. But in general, in the lab, if you're working around, you don't do things like that. So for the transmission case, the delta lambda over lambda is large, and the delta theta is small, okay? And when you replay, and for the reflection case, it's the opposite. The delta lambda over lambda is small, selective, and the delta theta over lambda is large. Okie dokie, folks. Now, have we got any questions about this now? This material? Any questions? So I know now I'm going at a fair whip here, but again, I'm kind of assuming I can put this evil diagram up in front of you and you'll have a fairly solid notion of what that is, because I took some time and energy to explain them in the previous class. I think you should know what transmission and reflection geometries are, and I've already said previously the sort of general characteristics we expect from them in terms of selectivity. And what I've done here is I've done two things, hopefully. I've used the Cognix expression, so I've shown why they're useful and why they're powerful, and I've used them to demonstrate that this selectivity changes between the two cases, and that we can use these to get very good first order expressions for them, and why that's useful in terms of calculating things like how many transmission gratings you can store in a layer, or for example, in the case of reflection gratings, if we have a filter, how far away we drop before we get the first zero, so how rapidly we're going to fall off and move off Bragg. So we're going to lose the transmission capability. Okay, so is everybody happy with that? Any questions? Okay, if there's no questions there, then I can move to the next lecture. Okay, I'm just going to bring this up here to the top, excuse me. I just want to make sure that I actually did, excuse me. This one here, come down to here, okay. So this lecture here, okay. So again, I always like to start out by just revising things, the physical nature of things. And this is what I'm going to stop with today. I'm just going to talk a little bit about polarization, and then we'll have a little time for discussions at the end. So we do some revision about polarization first, and then tackle the problem of replaying and grating with light not only of TE polarization, where the E field is parallel to the surface and parallel to the fringes. Okay? A grating with light, not only which we have been working with so far, so both in terms of our exposure and our replay, we pretty much always assume that the E field had a particular orientation with respect to the grating. And in the case of the exposure, we want to get the maximum fringe visibility. And in the case of replay, then we just find that the maths is actually easier when we look at the TE because of the orientation of the E field with respect to the permittivity variation. As part of our derivation, we made an assumption about that orientation. We took the fact that the E dot, the gradient to the permittivity, or the was actually 0, okay? And now we're going to have cases where that's not necessarily true. And again, this is covered in Cognix, and I'm going to sort of expand a little bit in Cognix, and it's also covered in SIMS. And polarization is a pretty fundamental thing that we need to know about in relation to these gratings. And because there's an orientation here, we're going to have to talk about the orientation of the electric field with respect to the actual grating. Today we'll do some revision about polarization first, and then tackle the problem of replaying grating with light, not only the depolarization. That's what we've been looking at so far. To start our revision, let's just first recall the Fresnel reflection and transmission coefficients. So again, I'm assuming you guys have seen stuff like this before. This isn't going to come as some big surprise, but I know that you met it in a course maybe a while back, and so it's good to just revise it to remind you what's going on. So I'm using a typical sort of engineering notation when I talk about TE polarization and TM polarization. And I think I mentioned in an earlier lecture that you can have a huge range of, there's a huge number of ways you can actually talk about polarization and the orientation of polarizations. So I'm talking about a situation here where we have a plane, we have a normal to that plane, we have an incident beam, a reflected beam and a transmitted beam, and we're assuming here that this medium up here has a lower index than this, so this angle in here is less than the angle up here. We talk about the angles of incidence, and they refer to the angle between the input beam and the normal to the surface, the dashed line. And in terms of polarization, we're talking about the E field pointing out of the page. So we have a circle here with a dot in the middle, and that indicates that the E field is pointing out of the page. And then perpendicular to it, we have the H field, okay? And so we have this direction of flow, vectors pointing out of the page. Now, if you look at this, you'll see actually that this is not consistent with the pointing vector, because E cross H should give me the pointing vector. So we just think about the E field here is oscillating in and out of the page, and the H field is oscillating up and down perpendicular to it. We're not too worried about the pointing vectors at the moment. Similarly, we could have a beam which is incident like this. And again, we see there's no change in the Snell condition. We go from the epsilon, the permittivity number 1 to permittivity 2. And we've got permittivity number 1 is less than permittivity 2, so it's exactly the same situation. But now what we've done is we've actually rotated our field. So we have the E field here pointing up here, perpendicular here, and now the H field is pointing. In this case, we've got it pointing. I can't see if it's a cross or a dot, but let's assume it's pointing out of the page. If it's pointing out of the page, then we actually have consistency with our pointing vector. That E cross H gives us this particular direction for our pointing vector. And we see now that these two are different. The orientation of the E field with respect to that surface. And if we have fringes in here, we're going to see that the orientation of the E field with respect to the fringes of the grating component, grating vector, are going to be different. And because of that, we're going to change the results. If we look at our Fresnel reflection coefficients, for this case, we match our total E field above to the total E field below, and the total H field above to the total H field below that boundary. We can come along and we can find out reflection and transmission coefficients. And there's a lot of different ways people write down these Fresnel reflection and transmission coefficients. And here I've written them down in terms of the refractive index. Typically, engineers would write them down in terms of intrinsic impedance of the medium. So the square root of the permittivity divided by the permeability. But here we've shot through that and we've written it down in terms of refractive index. So square roots of the relative permittivities in the medium. And this is the refractive index in the second medium, the higher refractive index. And this is the lower refractive index in the first medium. And then θ1 is the angle of incidence, and θ2 is the angle of refraction. And we can relate those two via the Snell's law. So we have, if we have an input field, we multiply it by this and we get our transmitted field. And if we have an incident field, we multiply by this and we get our reflected field. And for the TM polarization, we see they're different. The coefficients are different, okay? We have a different set of coefficients. It's N1 times cosine θ1 here. It's N2 times cosine θ1 here. So there's a difference. There's a mixture up between these two things. Snell's law is valid. N1 sine θ1 is equal to N2 sine θ2. For the reflection coefficient, it can be shown that there exists an angle of input called the Brewster angle. This is going to come up later when we talk about our gratings, but we can have an angle of incidence in which the reflection coefficient is equal to 0. There's nothing reflected. So we can find a case where this here is 0. Effectively, when this is equal to this, and this coefficient becomes 0, and therefore nothing is reflected, the Brewster angle. There's no reflected beam. And we showed this response plotted in the diagram over the page. All of these laws hold for isotropic materials. So here's our reflection coefficient. here. This is our TE and this is our TM. And for the TE intensity of the reflected light, we see we start off here, and for glass, this would be something like 4%. And this would increase up, and at 90 degrees incidence, everything is transmitted for the TE case. Sorry, reflected, everything's reflected, excuse me. For the TM case, we start off with the same value as the TE, because we can see here from our diagram that if we are normally incident, if we're normally incident, both of these are the same, because this here is a 2D surface, and if we're normally incident, the E field and the H field are both parallel to the surface. And if we go from a high medium to a high index to a low index, so this is from a low index to a high index, this is from a high index to a low index, then basically everything is squashed, because we have a total internal angle of reflection. And so our TE again goes from 0 up to 100% at the angle of total internal reflection. The TM once again has a Brewster angle, goes to 0, and again it's going to increase then after that and go up here. This again is the magnitude squared of those reflection coefficients. Effectively, if we were to plot out the coefficients themselves, we'd see here that in the TM case, we actually have a change in sign. So we have a phase shift here of 180 degrees, a sign change. Some of you also will have met this notion of anisotropic material and anestropy. So the idea that you can have crystals where the fields pointing in the different directions experience or see different refractive indices. And so you can have a perfectly isotropic type material where essentially there's no phase shift between different orientations to linear polarization of the light. You can have materials where you have a positive shift, a change between the two, and also you can have more complicated situations depending on the orientation of the optical axis, where you actually get separation of the two beams. I'm not going to spend a huge amount of time about this, but it turns out that gratings are effectively these sort of anisotropic materials. They're no longer isotropic. So, and people spend quite a bit of time talking about this. So I'm going to just mention this briefly. It's not in Cognix. It's talked about a little bit in SIMS, and I just want to make you aware of it. Let's now quickly do some general revision about polarized light. First, let us recall the term plane or linear polarization, circular polarization, and elliptic polarization. So this is very much a very quick little tutorial. And again, it's a little bit about me introducing notation. Assume our K vector lies along Z, so it's perfectly along Z, then the E field will lie in the XY plane, and we can choose the X and Y axis to correspond to the TE and TM polarized cases respectively. Okay, so we have linear polarization, and we can rotate that linear polarization. In terms of actual optical tables, typically the output from your standard laser has a linear polarization, and often that linear polarization is actually chosen so that it's in the vertical. Okay, no, you can easily buy polarized rotators as well. But it makes the orientation and choice of orientation fairly straightforward. In fact, most components you buy, if they have an element of there's polarization effects associated with them, they come pre-built. You buy a box and it's automatically set up so that it has a particular alignment with respect to your standard laser beam alignment coming out of the cavity. In time, both components of the E field will vary harmonically. Okay, so you can have something which looks like this. You've got amplitudes, you've got sinusoidal variations with respect to time, and you've got an orientation. Okay, and if the E is in the X direction, we can call that TE, and if the E points in the Y direction, we can call it EY. If it's linearly polarized, we can have linearly polarized beams where the actual E field has components in X and Z, for example, X and Y, excuse me. But the two components can be varying with respect to time. And omega is the frequency of the light, T is time, and this delta is some phase shift between the two components. The magnitude of EY is given by this, which substituting for the omega T terms, the magnitude of E gives us this here. So we end up with an expression which looks like this, and this basically is the equation of an ellipse. So we have the idea that if you like you have the directional propagation, and if you look at the point of maximum E field, you'll find that it actually rotates in space. You'll have a variation in space, and in most general case it will rotate, it will form an elliptical type variation in space, and reduced from that it's circular, and reduced from that further is a linear variation. If the two components have equal and the delta 0, we're going to have these two things being equal in this case, and we end up with something which is circular or linear. If there's no phase shift, it's going to be linear. So for plain linear polarization, if EX is equal to EY is equal to E, the ellipse becomes a circle. We got the delta as this form. We have this is the equation, and so we have these. This is our formula, which is equal to 0. It's a radius, E. Should be noted that for the case of elliptical polarized light, the two components are mutually perpendicular and coherent. And classical representation of the evolution will be something like this. We introduce various phase shifts between them. The path that's actually followed by the E field, the maximum or the direction of the E field is something like this, and we can evolve, we can cause an evolution by introducing various phase shifts. We do this using something like maybe like an electro-optic modulator. It should also be noted that the intensity of the polarized light will always equal the sum of the squares of the amplitudes of the perpendicular components. So this becomes particularly interesting or useful if you want to, for example, reduce feedback into a laser cavity. You can introduce a thing called a Faraday Rotator, where you take the linear polarization that comes out of the cavity, and any light that's reflected, by the time it goes through the Faraday and comes back, it's actually oriented at 90 degrees to the original polarization, and therefore doesn't affect the operation of the cavity. That would be a fairly standard operation or use of an electro-optic modulator that has this sort of phase shifting capability. By changing the phase shift between the components, we do not change the intensity of the beam. A material which changes delta is called an anisotropic material, and I just note it may change other things as well. What is an anisotropic material? Well, the full answer to this is very complex, as there are many different types. And you can go away and you can find lovely books about crystalline structures and all sorts of weird and wonderful type materials. Generally, you go away and you can buy something which is a fixed phase shift, and it comes in a box. And as I said, the box is built so that it orientates to standard lasers. And you may have external drivers, so you can actually cause this thing to vary with time. Electro-optic modulators. Many different types and forms of anestropy. And you can, of course, have liquids that have anisotropic material, and liquid crystals generally do, because you've got some sort of alignment process inside there. However, very simply, an anisotropic material is one in which different directions within the material have different refractive indices. And this is usually explained sort of in a very hand-waving way by stating that just like a ball suspended by 6 springs inside a cube, an electron can be assumed to be attached to a nucleus or within a crystal in a similar way. So it's restrained in various different directions, and the stiffness of the springs in the different directions can change, and therefore the ability to cause that electron to move or that particle to move up and down or left and right will vary depending on the direction, the relative orientation of the driving function. So if it's a charged particle and we've got an external electric field, the orientation of the electric field with respect to the directions of those springs will produce different amounts of motions at different types of directions, and therefore result in different types of refractive index. This is very hand wavy, but again, basically that's what the sort of thing that's happening. It's also a very classical picture, but I think you see what I'm saying here. So the springs are like the components of the electric field potential around the nucleus. As the stiffness of the springs in any direction changes, the frequency of natural mode of oscillation of the sphere in that direction also changes. An electron hindered in this way would, if excited, not give a perfect symmetric scatter field corresponding to an isotropic material. So in an isotropic material, the springs are the same in all directions, and irrespective of the direction orientation of the E field, you get the exact same effect of the actual electron. It does the exact same scattering or interaction between the fields and the electrons, and the exact same result outputs from the electrons in all directions. It's isotropic. Corresponding to it. In fact, because the incident or excitation light in a transverse wave, the different components of this wave, T, TMP polarizations, will be affected by the structure in different ways. So you have a field propagating with a K vector, you've got an orientation of the E field with respect to that K vector, and depending on the direction of the K vector and depending on the orientation of the E field with respect to a particular material, you'll get different effects. And I try to illustrate this above with this electro-optic material, where we've got basically these planes, the optical axis, which is related to the orientation of the springs, and then we've got different orientations of this optical axis and different orientations of the actual E fields, producing quite different results. Okay. Okie dokie. Okay, let's very carefully and simply examine the case of uniaxial birefringent crystal, and holograms that we've been talking about are like that. For this case, if we choose our axis carefully, we can get nx is equal to ny is equal to n0, the ordinary axis, and nz is equal to ne, or the extraordinary axis. So I put this in here basically because I want to give you some basis for the actual fact that polarization is important. For those of you who are familiar with this type of material, this is maybe a nice little reminder. And for those of you who haven't met it yet, it sort of prepares the ground a little bit for things you're going to see in future. Light traveling parallel to the z-axis, both T and Tm, will have E-field components which only see N0. So the E-fields will point in the X and Y direction. They're only going to see this refractive index N0. Rotation about the z-axis will not change this. This direction has some significance and is usually referred to as the optical axis. And you can have materials which have no optical axis or have one or have two optical axes, which is the most general case, well, for standard crystals. Because for this material, there's only one such axis is called uniaxial. The birefringence of the material is defined as the extraordinary index minus the ordinary. If the extraordinary is greater than that, we've got a positive birefringence, and if the extraordinary is less than it, we have a negative birefringence. Suppose we now have light traveling along the X or Y axis. So now we have a different case, because now our E field is going to be pointing in, if it's traveling in the X direction, we're now going to have an E field pointing in the Y direction and potentially another E field component in the Z direction. And those two components are going to see two different refractive indices. In this previous case, the E was in the X and Y, and therefore both cases had indexes of NO, ordinary, and therefore they both saw the same index. Now we have a situation where the two polarization, if we've got components in the two directions, so if we're traveling in X, we now have an E field component in the Y and in the Z, and both of those are going to see different refractive indices. So we're going to have a phase shift difference between the two. They're going to travel with different velocities. The E field for this light can be split into two components, polarizations, one parallel to Z with the index NE, and the other in the XY plane with an index NO. Both polarizations will have a different wave vector magnitude or phase velocity. The wave parallel to Z will have Kz is equal to beta times Ne, and so the wavelength in that direction is going to be the wavelength divided by Ne, and the one in the XY plane will have K is equal to beta N0, or a wavelength which is the wavelength of free space divided by N0. If both beams travel a distance d through the material, then the phase difference between them at the output is given by this: 2 pi over the wavelength times Ne minus E ordinary times d, or beta d times delta n. That's the phase shift, the delta phi maximum, where delta n is our birefringence. Obviously, light not traveling along the optical axis or perpendicular to it will have its two components, the two TE and the TM components, the orientations of the field, the two perpendicular orientations of the E field, phase shift with respect to one another by the amount between 0 and delta phi max, okay, depending on the thickness. It should also be noted that since the two components see different indices on entering the material, they will both experience different angles of refraction inside the material. Okay, we're going to get different, and to find out this, we have to do phase matching across the boundary. Okay, and in the case of anisotropic materials, we're going to find a birefringent materials. What we're going to find out is that we're going to have different boundary conditions, different reflection coefficients as well, depending on how the field is oriented on the actual boundary inside the mirror. Since finite beams of light are used, so we talk about plane waves, and of course we've got infinite plane waves, and we have them incident on an infinite material, then the waves that are coming out of the other side are going to be infinite. But if we have finite beams, we'll actually see the fact that we get this shifting of the finite beams. And the most famous example of this is Icelandic spar, yeah, where you actually look through it and you actually see two images because of this effect. Again, you can look that up. Anisotropic material. In fact, in general, the power in the ordinary wave will travel in the normal direction. So we have our standard pointing vector E cross H, which is parallel to K. However, for the extraordinary case, in general, the power in the wave does not travel in the wave normal direction. Okay, it doesn't travel in the wave normal direction. So here is a fairly here we have a K vector, and here we have a pointing vector, and the pointing vector is not collinear with, it's not parallel to the K vector. In general, we would expect it to be so in free space, and in plane waves, it is the case that these two are together. But in this case, what happens is, and students often, when they first meet Maxwell's equations, and they see us using the density, electric field density is equal to the permittivity times the E field. And the permittivity is a constant. And people wonder, why do you bother having electric field density? And this basically is why. Because in these materials, what happens is you don't have a constant value permittivity anymore. You've got a matrix. Your permittivity is a matrix. You have different permittivities in different directions. And so you have a significant difference between the direction or orientation of the E field and the direction and orientation of the D field. Okay? So we have a direction, but we have a difference between the direction in which the phase fronts are oriented and a direction in which the power front is oriented. And so you can have a situation where you have a plane wave incident on a surface, and you have, here's our beam coming in, and here we have an ordinary wave coming down, which may well be, for example, Snell's law. But you can have another phase front, and you see both of these are phase matched along the boundary. We've got our red phase front and our blue phase front down here, and all of them are here. If we've got a maximum in our input, we've got maximums here, but there's a different tilt, and therefore there's a different wavelength for the two different things, and it's a different velocity when we cross the boundary with an anisotropic material. All the beams are phase matched across the boundary. Okay, now I can stop there probably quite handily, and then I can come back to holography later. And I know, as I said, some of you have met this before, some of you may not have met this before, you may have met in a different guise. I just want to make sure you're familiar with this terminology and some of these words, because I'll probably refer to some of these things. I refer to them a little bit later on when we talk about the holograms. Okay? Now we're about a quarter to the hour. Has anybody got any questions or queries? We did quite a lot of stuff today, but I have to say a lot of the things we did were repetition. Okay, so a lot of the things we did were things that we'd done in previous lectures and talks. Okay, so we repeated things. We repeated a lot of different things again. Yeah, we didn't, I wasn't all new stuff. It was little pieces that we did were new, but a lot of it was repetition. Okay, so I hope I didn't talk too quickly, and I hope you could follow what I was doing here. Is everybody okay? Hello? Is anybody there?
Yes.
Yeah, of course.
Yeah, sure.
Yeah.
Okay, so here now, this now is a query. So okay, so I asked the staff in ITMO to schedule a lecture for tomorrow morning. Okay, and I did that because I wasn't quite sure how fast I'd be able to get through the material. So I asked for lectures on the 2 Saturday mornings. Okay, now I'm quite happy. I think we're doing quite well on the lecture material. Okay, so far. I don't know what you think. What do you think? Because, for example, we can meet tomorrow morning and I can review material, and we can meet tomorrow morning, I could do new material, or right now I don't think we need to meet tomorrow morning. Yeah? I only asked for the Saturday lectures in case I was going to be stuck for time. And as far as I can see, I'm pretty much on time for what I want to do. Now, we may have to have the lecture next Saturday, but it's really up to you guys. What do you think? Do you want to meet tomorrow morning?
Well, let us ask the students maybe.
Yes, that's what I want to do.
Yeah.
And I'd really love it if every student said something.
Maybe we don't have to meet tomorrow morning if you think we are not going to be left with some materials we didn't have time to study.
Okay. Okay. I mean, I still want to keep the lecture for the following Saturday in the schedule, because again, there may be some last minute things I want to talk about with you. Okay.
Yeah.
But for example, tomorrow, as I said to you now, we could just meet and we could talk about the material I've already done if you have questions. Yeah. Or I can do new material tomorrow, or we don't have to meet tomorrow. Now, I don't know about Russian students. Irish students are terribly lazy, very, very lazy. And so if you tell Irish students they don't have to have a lecture, they always say, hooray, and then they run away to drink beer, okay? Now, I know Russian students are much tougher, yeah, much tougher, okay? But I do not mind. And as long as ITMO does not mind, we can have a lecture, but we don't have to have a lecture. So if everybody says, no, if you're happy, we're happy not to have a lecture, then that's okay for me. So we have at least one student who thinks it's okay not to have a lecture. What do the other students think?
I guess I agree.
Okay.
If everything okay.
So we don't have a lecture.
Yeah.
Okay.
But of course, the students have to be aware that they have to pass an examination afterwards.
Yeah.
And it might be good to discuss some things which are not yet completely clear, but
Sure.
should be up to the students.
Students.
Maybe we make a vote or something like that. Maybe those who want to have a lecture tomorrow or a meeting with Professor Sheridan, they may raise hands.
Yeah.
Is there anyone of the students, any of the students who would prefer to have a lecture, to listen to attend the lecture?
If they're very embarrassed, they could just send an email. Yeah, I don't mind how they decide.
Yeah, okay.
So, I mean, but please let me know beforehand.
Maybe not immediately before the lecture.
No, maybe not. No, maybe not 10 minutes before. Yeah, I think we had a starting time which was 1 hour later. Yeah, so 9 o'clock my time, and I can't remember, maybe 12 o'clock your time. Yeah, but besides that, I think it's all the same. Yeah. I can't remember the timetable, but I'll check up whatever the official timetable is. It may be the same time. I can't remember. Okay, but please just send me an email this evening, and then I will show up or I won't show up. Yeah, and I'm quite happy to show up. I don't mind.
Okay, but so far we don't see the need to have a lecture tomorrow.
Okay. So that would be the default position. Unless I get an email telling me there is a lecture, the default position is there is no lecture. Okay?
Okay, fine.
Okie dokie. So I hope everybody is looking at Cognix, and Cognix is, I think it's quite a dense paper. And then the other work is Sims. And really, if you can look at Sims, you'll find that I follow very much his pattern. Okay? So we have a little bit more to do now with electromagnetism. And then I'm going to move on to look at materials, okay, which is very different. But I want to do this work because I think it's a great practical value to engineers, okay? Is that okay?
Yeah, obviously.
Okay, folks. So if there's no questions, please, I'll see you, I think next Monday. I can't remember exactly, but if we don't meet on Saturday, I think it's next Monday. Okay?
I'm sorry, can I ask you the question?
Sure, please.
It's not about the lecture, it's about the organization. Can the administration of this Zoom call allow students to record the lessons? Because I like to review the lecture right after it ends to make some notes.
So the lectures so far, I've received links for 2 YouTube movies. Yeah. So I assume that the staff and ITMO are circulating the YouTube links. So if you're saying it would be a very good idea if the YouTube link could be sent immediately.
Yes, if it's possible.
If it's possible.
When I'm listening to lecture,
yeah.
I'm not making notes. I'm trying to just capture because it's a little hard for me. And
I understand.
I'll watch the lectures again and make some notes to understand.
Very good. Yeah. So I would, if it's possible. So I do not send out the YouTube video. I don't have a recording. So it's the people in ITMO who record this. So basically, we are asking if the staff in ITMO could send out the YouTube link as soon as possible.
Yes, please. Thanks.
That would be good. Yeah.
Yes. Thank you.
You're welcome. And again, if you have any questions, if you're watching the video and you have questions, please send me an email. Yeah. I'm very happy to reply, or we can have a meeting on Saturday. Yeah.
Yes, of course.
Okay. Are there any other questions?
Yeah, I have a question.
Yeah.
And this is regarding this case of reflection and transmission holograms and the difference in their selectivity.
Yeah.
So one type is more selective in the wavelength for wavelengths.
Yes. So
another is for angles, right? So, yes. But actually, as far as I understood, the difference between reflection and transmission is in slant angle, in some sense.
Yes. So it's the orientation of the fringes.
Indeed, yeah. So does this mean that there is some slant angle that equalizes these two cases, so that which makes like wavelength selectivity and angular selectivity equal between each other.
So are there such cases? Yes. Okay. So I mentioned to you that, for example, you can actually, and this is something I sort of mentioned as a little exercise, you can take your evil diagram and you can put in a K vector. Okay. And you could imagine having a K vector which is for a very slanted grating. Yeah. And as I said, once you've made the grating, the K vector is fixed. And then you can replay that particular grating with beams angle at different angles. Yeah, you can change the angle of incidence of a beam. You could keep the wavelength the same, or you could change the wavelength, but you can replay with a different beam. Yeah, and what you will find out is that there are some K vectors which, if you replay them at one angle, they will behave as transmission gratings. And if you replay them at a different angle, they will actually replay as reflection gratings. Okay.
I see. Okay.
So in that case, you can see that basically, well, you're going from a transmission geometry to a reflection geometry because of the orientation of the grating. So if you've got a highly slanted grating, depending on the angle of replay, you can replay as a transmission or reflection grating, or you can change the wavelength. And in that case, what will happen is, if you look at the K vector, you can actually also show that you'll go from a transmission to a reflection grating. And in fact, you can even have an unbragged transmission and an unbragged reflection case. So the point is that, however, in the general sense, yeah, in the general sense, for example, of having a beam that's incident, let's say two exposing beams that are both have angles that are, let's say, 0 to 30 degrees or 0 to minus 30 degrees. And you orient them as a transmission where they're both incident from the same side, or reflection where they're incident from opposite sides. And so you very clearly have transmission geometry and very clearly have reflection geometry. In that case, the rules of thumb I've given are accurate.
Okay, thanks.
Yeah?
Yeah.
In fact, in most exposures, we'll talk a little bit about this, but when you expose most gratings, let's say a transmission grating, you're going to have some boundary reflections on the far side of the material. So you put the two waves in and they're create an interference pattern, and then they reach the interface, the other interface, the output side. You're going to get some reflections there. And in that case, you'd have effectively 4 exposing beams present. You have 4 exposing beams present. You have the 2 input beams, which are traveling forward, and you've got 2 backward beams due to reflections at the far boundary. And in that case, you can go away and you can say, well, how many gratings am I going to record? And basically, every one of those beams records a grating with every one of the other beams. And so you actually end up with something like 4 gratings. And 2 of those gratings are going to be reflection gratings. Yeah? Or 3.
Are they of considerable contrast, actually?
That's the point. You will have a variation in the contrast between them, the strengths of those gratings. But as we've seen, the strength tells you a lot of information, but the geometry also tells you more information. So for example, we could start off making a transmission grating, and we could go up to 100%. And then the reflection gratings would be relatively weak because you've only exposed for a certain amount of time. But then you start exposing for longer. And now you've gone over the maximum in the sinusoid and you're going down, you're reducing the efficiency on the far side of the sinusoid. But the reflection gratings keep on getting stronger and stronger. Okay? So exposing,
indeed.
So,
yeah.
So exposing for longer will make the actual effect of the transmission grating weaker and will make the effects of the reflection grating stronger. Now, the natural limit to this, of course, is the amount of medium, the response of the medium. Because, of course, eventually the medium will no longer be capable of recording anything. Okay? But you still have to be very careful.
Thank you. This is very practical, actually. Thank you.
I like to put things in terms that are really simple, if possible.
Yeah.
Okay. Everything has some consequence, and the problem is I don't know what application you guys will want this for, because you're going to go and somebody's going to ask you a very particular question, and in that for that particular case, understanding the fundamentals is going to be important. Are there any other questions? Okay, I'm going to assume that we're not meeting tomorrow. If somebody wants even to have a one-on-one tutorial or something, I'm very happy to come in and talk to people tomorrow, but I won't present new lecture material tomorrow, okay? If somebody just wants a tutorial, if all the class wants to have a lecture, we'll have a lecture, okay? So it's really up to you guys, yeah? Don't be shy. All right.
Okay, thank you very much. If the audience will decide to ask you to give a lecture, we'll ask you. We'll
exactly
write
exactly.
or somewhere somehow communicate with you.
I have a general policy, ladies and gentlemen. You guys are adults, okay, and you want to be professional engineers, okay. So basically, you get to act like responsible professional engineers. And if you want lectures, you can have them. And if you don't want them, you don't have them. You get to make a choice and a decision. I like that. Yeah, I like people to decide they want to work and to decide if they don't want to work and to decide what they do. Then if it goes wrong, it's their fault. Okay, it's not my fault anymore. Okay.
Okay, great.
Very good. All right. Have a good weekend. If I don't see you.
Bye.
Thank you very much.
Bye-bye.
Thank you. Bye.
Ciao, ciao.
Goodbye.